Today on the Ed-Detective, we're going to talk about multiple sequence alignments. In the example we looked at during our last class meeting, many of you realized that there were two different 3-nucleotide sequence motifs you could potentially use to align these 5 sequences. Here, we're looking at the CTT motif, and here is an example of the 5 sequences aligned on a different motif, the 3 nucleotides TGC. Here we can see that aligning on TGC is not as good because the flanking nucleotides, positions 5 and 9, the way this alignment has been numbered, do not really generate a solid consensus sequence compared to what happens when you align on the CTT motif, where now a solid consensus sequence develops among all 5 of the sequences we're trying to align. After class, a number of you have approached me to inquire about many points related to this topic. First, how to create a multiple sequence alignment. Second, how to number the nucleotides. Third, how to develop a consensus sequence. And most important, I would say, is the question, how do we know which alignment is best? Imagine that we have DNA sequences from the fox, the skunk, the bear, and the pig. And all we get from each of these organisms is some portion of the sequence of a chromosome. And the question that we want to ask when we're doing DNA sequence alignments is, are these 4 sequences related in any way? And that's why we look first for some sort of a sequence motif that might indicate which regions of this sequence are similar. Right now, if I asked you to generate a consensus sequence, you would erroneously look at the first column and say maybe A is most common, and you might look at the second column of sequence and say T is 50%, so that's most common. And the T in the third column, there's 2 out of the 4, and so forth. But that wouldn't be the best possible alignment of these 4 sequences. You can see there's no one column here at this point where all of the sequences share the same letter. That suggests that we haven't lined these up properly. So what we're going to do, as we talked about in class, is look for a particular sequence that all 4 of these sequences share in common. And I want to point out here that the reason that I put ellipses at the ends of these sequences is to indicate that there's more sequence in either direction of these sequences. So this is part of an entire chromosome that could be millions of base pairs in both directions. But when we get DNA sequence information, we only get it in little fragments. And that, again, is the process of creating these sequence alignments, what geneticists do to determine if we're looking at the same sequence from these 4 different species. So what I'm going to focus your attention on here, and this is absolutely a trial and error process. This is definitely one of those times when there isn't just one right answer. But I know from setting this up that I created a sequence, at least TATA, that all of these 4 sequences share in common. So the method of performing a sequence alignment is finding the largest possible shared sequence motif, and then you slide the sequences relative to each other to line those up. So now I've aligned the skunk and the fox sequences on that TATA motif. And now we can see that maybe that motif is a little bit larger because those 2 species now share that entire sequence that I'm circling with my finger, the laser pointer, in common. So now what we do with the rest of the sequences is also line them up based on that TATA sequence. And there's our final sequence alignment. We can see that we've got those 4 sequences aligned using that TATA sequence, but the largest motif that we have that exists is actually the G through the G. So G, T, A, T, A, C, G are shared by all of these sequences. Now, if I was going to number this alignment, what I'd ask you to do, although this is not something you have to do, there isn't a particular format for this, would be to number starting at the leftmost nucleotide. For example, we would start with the leftmost A in Fox being position 1. We do that in black. Position 2 is next, 3, 4, and so forth, usually across the top of the sequence. And then to develop the consensus, you look at the most frequent nucleotide at every position. So an A at position 1, a T at position 2, and in this example, all of the sequences from all 4 of these species match. So the consensus sequence we're going to build up is GCA. And again, we could disagree, and it's totally fine at this point what you do with the rest of these nucleotides, CTA, GTC, that are present in the skunk sequence but in no other sequence. You could add those to the consensus, that would be fine. Or you could argue with me that because there's only one copy of each of those nucleotides in those 4 species, that you don't have enough information yet to determine whether or not that's a consensus sequence. And again, that would be totally fine. So this is a great example of how there isn't necessarily one right answer. In this case, there is, but you can argue about some of the details, and if this was an exam question, as long as you argue from a scientific point of view, based on information we've discussed in class, I'm happy to give full credit to disagreements as long as there's a scientific rationale that's a valid rationale. To answer the original question, even geneticists with computer programs don't always know that they've found the best, most optimal sequence alignment. So, this is a trial and error process, and I expect that many of you will come up with different answers to the same question that I pose. Don't worry about this. I often grade based on arriving at a valid answer, not necessarily the best answer. Thanks for watching, and please be sure to be in touch if you have any questions.